So welcome from my side as well to today's presentation and to the start of this full series on materials for electronics innovation. We will start with materials in RF applications, so anything high frequency. Of course, this is a very broad topic, and that does contain a variety of different materials and classes. And in order to structure that and to understand the different requirements for application, it does help to look into the way that the wave is interacting with the material. And for that, we usually look at this either in a way of wave propagation, for example, in transmission lines where we have a conductive, so a confined transmission of a signal versus a radiated wave where we have an electromagnetic wave propagating, which is then interacting with materials. So for the conductive part, so a contained electromagnetic wave, you can see here on the slide, for example, on the left-hand side, we have a strip line or a microstrip configuration, coplanar lines as well, with a cross-section. And the main part of the electromagnetic field will really be in the substrate here. So if we talk about materials for high frequencies, that means here we mainly have to investigate the dielectric substrate that can be a composite containing polymers, but also standalone polymer films, for example, glass, ceramic, you know the drill probably. Since we're a packaging institute, that also can involve underfiller materials, or anything really that is in close contact to a conductive structure that's carrying a signal. So these materials have to be understood and also further developed. Second is the conductive material, often copper, but also the surface roughness plays a role, including surface finishes, passivation layers. So anything that is on the conductive part is part of the discussion as well. Here, the main focus is always to minimize the losses. If we move on to radiation, you see two examples for antennas, for example, microstrip or a coplanar configuration. You see that we do have the field within the structure as well, but this is very much like the conduction part as well. So this is kind of understood which kinds of materials are relevant there. But we have to add some as well. Since we have the radiation propagating here, that can also be housing material. Radomes, they are manufactured of a certain material. And not only the material itself, but also the setup, so the geometry, especially at the very high frequencies where the wavelength is becoming shorter and shorter. And finally, there is not only wanted radiation, but also unwanted radiation. So for example, if you want your circuit to be protected from external radiation, you would use a shielding or a housing that's coated with a shielding material, or if you have radiation within your system and you need to confine it in the volume so it's not propagating, because then you would get into trouble with regulations. So these are the kinds of materials that we need to understand and that are further and further developed. Now, if I could, today, this would be the outline, what I would think is the most important parts that should be discussed when we have a talk like that, a presentation like that. We need to start with the key markets. So what are the relevant markets for RF systems? What are the relevant markets for packaging of RF systems? So where are the trends and developments there? And we need to talk about the frequencies that are allocated for the various applications, and from that we can bridge it to the basic science. So we need to understand the materials from the physics of the build-up, starting with the dielectrics, for example, organic, inorganic, composites, then the conductive material. I also started to explain that. And what we should not forget is that all of these material properties are depending on temperature. And even further, today I will show one of our studies where we looked at aging effects and dielectric substrates. So it's not just that the properties change with temperature, but also with duration. So when you keep it at elevated temperatures over time, you will see drifts in the material properties. And in order to connect these basic understanding of the material to the application in the market, you need to characterize the materials. So this would be the natural next step. We need to talk about characterization methods, again, dielectric, conductive, and shielding. And here we can have a few spotlights on, for example, broadband characterization to get data rather quickly for broad frequency range versus the characterization of low-loss materials where you need a very high resolution and need to put an extra effort to that end. And probably what is definitely needed is some guideline, which characterization techniques actually suitable for which combination of a material and a specific application. And we could not stop there because actually in the end we would have to add some current hot topics like the PFAS regulations. I'm pretty sure that several companies in the European markets are really thinking about that right now, how to move in that context. And also a player that's becoming stronger and stronger is additive manufacturing. We see that a big company for RF laminates, which is Rogers, has put a commercial system out there for 3D printing of dielectrics, and also I think 2 years ago. So it's really there on the market now for the dielectric, and the same applies to the conductive material. We also see that the additive manufacturing technologies are advancing more and more, and with that we see better performance, because in the end the limit for the performance is the conductivity of the core material from the copper, for example, or the whatever material you use in your additive manufacturing process. And while this is proceeding, we see that we can use it more and more also for RF applications, where in the past maybe the quality has not been good enough. But I'm already 6, 7, 8 minutes into my presentation, so it's pretty clear. I cannot cover all of that today, so I cherry-picked a few items, which then looks a bit like this. So we'll look a bit at the markets in the next minutes, and then I will cross out almost all of the basic physics, even though I'm a physicist, so this is actually what I find most interesting. But I will at least put our study on the aging effects in here, because I think it's really an interesting development, and we're in discussion with material manufacturers how to include that in a standard characterization process. And of course, then we will talk about characterization methods, some guidelines, and at least the PFAS regulations, or the current state of it will be in the presentation today. So, getting started with the markets. Usually we look at 6 main markets, which is more or less a standard, I think, across the industry. It's mobile and consumer, automotive and mobility, telecommunications and infrastructure, medical, defense and aerospace, and industrial applications. And here I brought a nice image of our system. So we at Fraunhofer IZM, we do packaging and system integration, and you can see that there are many different materials and components involved there. And of course, each of these ones, together with the manufacturing technologies, have to be chosen well for the individual application. And from our point of view, there are 2 main drivers, and one is telecommunication. I will show some material on that, and I will put some information on materials for automotive radar, because for us, these are the 2 main drivers, while of course the other markets are relevant as well. So starting at telecommunication, we've seen the evolution from 3 to 5, now 6G, and we see that the frequencies are constantly rising. Actually, the next slide will be from an advisory board meeting on one of our public funding projects, where we had the first discussions how to proceed with the research for 7G communications. So we're already starting to put 6G more or less in a more applied way and moving away from the very basic research. So what you've seen in the past is here in this figure, you see that on the y-axis, you have a log scale of the frequency, so 1 gigahertz, 10 gigahertz, 100 gigahertz. to see a rough estimate of the ranges that you have. Of course, when the frequency is increasing, the range will be limited. That's always part of the trade-off. And you can see main applications here. But what is really interesting is which frequency range is really allocated. And we've seen that in 5G was mainly focused sub-6 gigahertz, even though we do have millimeter wave bands at, for example, 26, 28, up to 39 gigahertz are different discussions about applications, but it's not that deep in the market yet. And what's currently in discussion for 6G is mainly what is also called the S3 band, so a mid-frequency range from 7 to 15 gigahertz for the nearest future, and then later together for very, very high data rates, the sub-terahertz bands, so above 100 gigahertz. And just to give you a feeling where in the timeline of 6G we are right now, I brought this one slide from our advisory board meeting. It's actually from Nokia Bell Labs, and it's a public slide, so I can include it here. And I know it's a lot of information, but I'd like to put your attention to mainly this red line here. And this is where we are right now. We are in fall of 2023, and you see that with this orange bar, we're moving from pre-standardization, basic R&D, now really towards the standardization process of 6G. And as soon as this is defined, everything will fall more and more into place. At least we have seen that with the previous standards, and it will be seen here as well. We expect that first the lower frequency bands will be standardized. So what I just said, 7 to 15 gigahertz, and that the frequency bands beyond 100 gigahertz will be assigned or standardized towards the process of 6G. And as you see here, the timeline goes up to 2030, apologies. And with this, I would like to close the communication systems, because now we know which frequencies we have to expect, and we know what to look for in the materials. And I like to add the automotive radar aspect for that. And here again, you see a number of slides, and I'd like to start on the left-hand side, because there you see that the growth rate is really there in the automotive radar. It has been for years, and it will stay. We really expect that there's a solid growth every year on the radar systems, not only by improving them or improving the numbers, but also by diversifying different radar applications within the automotive sector. What you see on the upper hand right here is a graph that has a yellow and an orange contribution, and the orange part down here is a radar that is at 24 gigahertz operating frequency versus the yellow one, which is 77, 79 gigahertz. And the timeline goes from 2015 to 2027. And what you see is really that the 24 gigahertz radar will be diminished more or less. At least this is the perspective from the industry, and that we see more and more the radar systems that have really elevated frequencies. Actually, in research, you already see 84, 91 gigahertz radars, 122, 140 gigahertz, and when you move away from the automotive application towards sensing-related applications, you see systems even beyond 200 gigahertz. So if we combine these two aspects, the communication aspect with the radar aspect, we'll really see that there is a need for highly integrated systems with specific materials over the wide range of frequencies, starting, as I said, sub-6 gigahertz, but really then 7 to 15, then starting of the millimeter wave, mid-millimeter wave with the radar systems, and beyond, even for both. One interesting aspect to add here is that for the radar platforms, we were located in Berlin. This is for us really interesting because the global market leaders are really European companies. So out of the 8 worldwide leading companies, 6 are actually located in Europe. So this millimeter wave market is really important when we do material science and materials optimization here. Last item to add here is that one technology from the RF point of view is really important, and this is the antenna on package concept. So that you no longer have a system that's creating your signals, taking care of your signals, processing your signals, and an antenna, but that you really integrate the antenna on or even within the package, and then you will see some different demands for the materials, because you can now see you will no longer optimize one material for signal process in conduction, but you also need to make sure that the system is working when it's also radiating. And actually, a trend that we see here is that there are options to reduce the number of processes required when you reduce the number of materials. So you can see first materials appearing that are available for every step of building up a system, from integration to a redistribution layer to actually antenna substrates. And this is really beneficial. If you do not have to mix your materials, and with that the technology for processing it and building it, in order to build a system and package with an antenna on package integrated. So this is a really important aspect when you want to understand where materials developments are moving, especially for the dielectric materials. Now, dielectric materials, I just said it. So what are the important parameters? I think probably everybody who's in this call knows the important parameters are the dielectric constant and the loss tangent, so dk and df. Here I brought one example slide from one of the projects that we did a while ago. It was a Horizon 2020 project. On the left-hand side, you see our system integration platform with our patterns that was utilized. I'm not going into detail here. What we need to look at is the antenna. And in the center, you see how this antenna was built on a PCB material. And at this point, it becomes really clear why the dielectric properties are such important parameters. Because you see on the right-hand side, there's this black curve, which is the original antenna performance. And maybe you've seen that the antenna has these slots, and all of this extra design effort is done to have a very broadband antenna to cover really a broad frequency range. And this was designed for a millimeter wave system at 39 gigahertz, and we can see excellent bandwidth. Now we could play with that in the simulation and increase or decrease the decay value. And of course, when we build such a system, we characterize the material. We know the decay value very well, and we can set up that it's functioning. But what would happen if, for some reason, the decay would be off? And you can see that with these blue and green curves, if you or increase your decay by 10 or even 20%, the resonance frequency starts to shift. And 20% is already enough that you more or less have no overlap more with your original resonance curve. And that's a problem because, as I said, the whole design is made in such a way that you want to have a broadband response. But if it's drifting or if it's even off from the beginning, that is a big problem. So this is why the dielectric parameters are such important factors here. I've shown that for an antenna, and now I would like to add even one more example on that. Because if you consider the system at 39 gigahertz, and now you envision we go for beyond 100 gigahertz, maybe for a radio or in this case a communication project and system. And here what you see is a IC embedded in PCB was from our 6G COM project. And you see that we have quite a signal path here. And remember, beyond 100 gigahertz, your wavelength becomes shorter and shorter. So your signal path is no longer transparent. You really have problems if you have mismatches. And the mismatch can come from not optimum design, or when your material parameters are off, or if you have a suboptimal combination of materials. So it's a really, you really need to put in the design effort here. So in this case, your signal path would contain a microstrip line from the IC. You will go over the RDL. You have several vias, different materials, so PI, and then your antenna substrate. And what's the most important message on the slide is for the complete D-band, speaking 110 to 170 gigahertz, we have really, really low losses here. So we can get a very high percentage of the signal up to the antenna, and we have very low reflection as well. So it can really be done. And proper control of material and process is really the key if you want to move to the systems that are at such high frequencies. So which materials should you choose, or what materials do the customers expect if you're a material manufacturer? And I just selected examples. This is really not a complete picture, just some idea. On the right-hand side up here, you see a diagram where on the x-axis you have the decay, so the dielectric constant, and on the y-axis you see the losses. And, oh, apologies. And you see that one of our, the material that is really liked by RF engineers is PTFE. Actually, the only material any RF engineer likes better than PTFE is probably air, but that's a challenge for packaging to do it only in air. So yeah, PTFE, very low decay, also very low losses. And here are a number of different materials where you can see actually low decay values, anything below 3.5 is probably usable, but then the losses are really increasing. Now for organic laminate materials, what you can see is here also on the left axis decay, right axis DF, and just some examples from this study here, what is available on the market. Now the question is what is really needed by the designer. And of course, as I said, often, especially for communication systems, you want to have a low decay. That has good reason. But often if your decay is a bit higher, you can compensate for that to some degree. But the one thing that no matter if it's communication or radar or any other applications, probably on the same page as the losses have to be low. So this is really crucial, especially when you think about system design, where often you cannot adjust it linearly. So if you have a bit more losses, you cannot just have a bit better amplifier or a bit extra of something. Sometimes you really have to have another module. So it's integer steps in your system components, and you cannot compensate that much for design. So the losses are becoming really a crucial part here. And speaking of the losses, that brings me to the one material science slide I really wanted to put in for today, and this is you do not have to choose the material just for the initial values. As I said, the decay and DF numbers are dependent on temperature, but they can also be dependent on duration of application. And we had a study on that. I just quickly summarize what you see here. So what we did is we took RF compatible material and we put it into accelerated aging. And then we did a number of tests. So as you see on the top here, this is just the color change in the material. We did mechanical test, warpage test, DMA, CTE, and also we tested the dielectric constant and the losses, and we did build antennas of the material and aged the antennas to see how the resonance frequency would actually shift. And based on this concept, you can define what we call a safe area of operation. So it's not just picking the original material, but also understanding what is the need from the end application and for how long your material will support that. And if you have that knowledge, you can even go one step further. Because if you know that your decay, for example, will increase a bit with time in your direct application, you know that your resonance frequency will shift. So you can design it in a way that it will be operational for as long as possible. It actually can be a bit first get better and then get worse. So this is another aspect, especially in combination with the reliability aspects that we are investigating here in-house. Now, how do we test these dielectric materials? And since I don't have that much time left, I try to speed up a bit here, apologies. So this is the characterization classification. So you always need to understand, as I said in the beginning, what is the application, what is your material, what is the use case? Is it a substrate where you will build a circuit on top, or is it more, especially, for example, a housing or a bumper material that's just in range of your radiation, but not really carrying a circuit? And based on these needs, you can choose the characterization method that you want to use. And I have 3 examples here to explain that. First is a free space method. You have 2 antennas, and these are mirrors here in the back and in the front. And in the center, this is a wafer of a mold material that we investigated. And then you can measure this mold material, and since it's a broadband antenna response, you can get with one set of antennas, one of these lines, for example. So you get a very broadband characterization rather quickly. But since it's a what we call transmission method, it has limits in resolution. So this kind of method will not bring you quite far if you, for example, characterizing like Eric said in the first introduction, ABF film. So you have a thin film standalone polymer, and it has very low losses. You will simply not see it. And also you will not be able to manufacture a sample that's big enough for that. Same applies, for example, for underfiller materials. This wafer has a diameter of, I think, 14 centimeters and a thickness of 1 millimeter. You will not make such a sample from an underfiller for various reasons. And this is why there are different approaches to characterize each material at the required frequency. One for the thin films with low losses, for example, is called an open resonator or Fabry-Perot resonator method, which you can see on the right-hand side. So you have a mirror on the top and a mirror on the bottom, and in between, actually, this is just an example film. It's orange is the material under test, and this is some data we collected over time, so it's really reproducible here for an RF laminate, 68 microns from 70 to 140 gigahertz. A very high resolution as well, because especially in the losses, you need this 4th digit, and this 4th digit in the losses is nothing you can get, for example, with a free space, but with such a method, you can get that. Now, if you want to move even closer to application, you can go for a structured characterization. So you would have your material under test and build a conductive path on top. And due to the shape of the conductive path, you can create a resonance. And this is seen here as an example characterization at 140 gigahertz. And what you have is this resonance, and this can then be evaluated. And from the location of the peak, you get the decay, more or less, and from the bandwidth of the peak, you more or less get the DF. Of course, it involves a bit more of analysis, but this is more or less how this principle is working. So you again have a resonance and then some interaction with your material. And this is how I would like to wrap up for today. So we talked about what are the applications, what are the frequency ranges, why are the decay and DF values so relevant, and I presented a selection of methods. Now, we are quite busy with characterization of materials right now, and this is one of the main reasons. So just a reminder, PFAS regulations on the way. Actually, the consultation of this process ended in like a month ago, in September 22nd. So now we're in a waiting period. It turns out that more than 4,000 organization companies and individuals submitted opinions to the committee, and there were more than 5,000 comments. So the consultation phase has summed up now, and until 2024, there's not really much more to do. So right now we're waiting, but from our analysis and point of view, it's very likely that for electronic materials, the PFAS restriction will be quite broad. At least in the original proposal for the restriction of PFAS, there was no exception for electronic materials. So yeah, we're really looking into alternatives, working with material manufacturers to get such low losses as, for example, PTFE has given us, but without the environmental and health impacts. Okay, One quick reminder, I said in the beginning, there's an outline, there's so much more to the topic, but of course we want to restrict ourselves a bit today. So just an advert here, we have end of November, so in a month and a bit, a workshop on site in Berlin, where we have 1.5 days, 2 days time to really talk about these issues, look at the instruments, go into detail. So if you're interested, just register or contact me, contact the colleagues in the call. And with that, I thank you for your attention.